What I'm going to be talking about today is Le Chatelier's principle and how it applies to the lab that we're going to be doing. So in your book, you have a table that lists some different stresses that reactions can undergo. Those stresses can include adding reactants, adding products, removing products, changing the size of your container, and changing the temperature or adding a catalyst. And each one of those stresses to a chemical reaction will result in a shift in the equilibrium. So you can choose to memorize the table that's in your book, or I have a different strategy that can help you get to the same answer. Let's look at the example, oxygen gas in the presence of heat turning into ozone. And I have listed here several different stresses that this particular reaction is going to undergo. So the first stress that we're going to look at is what would happen if we added more oxygen gas to our chemical reaction. So if we add a reactant, our table says that the products or the forward reaction is going to be favored. But I want to show you a trick that you can use without knowing this table. In a chemical reaction that's an equilibrium reaction, reactions always want to get back to balanced or get back to equilibrium. So we can think of a reaction in equilibrium as being like a balanced seesaw or teeter-totter. If you add more reactant, that's the same thing as adding another kid to the reactant side of your seesaw or teeter-totter. That's the stress. The question isn't asking us what happens when it's stressed. The question is asking us what has to happen for the reaction to get back to equilibrium. Well, in order to get back to equilibrium, you have to end up with more products. And the only way to get more products is to shift to more products. So when you add more oxygen, your seesaw or your teeter-totter shifts down, meaning that we make more reactants. To get back to equilibrium, your reaction has to shift in the opposite direction, or it has to shift towards the products or the forward reaction. That's exactly what our table here tells us. Let's look at what happens when we remove ozone. So again, we have our seesaw or our teeter-totter and it's balanced. If we remove ozone, that means that we're removing products. So if you remove a kid from a balanced seesaw or teeter-totter, then that means that the product side is going to go up. It has less weight than it did before. So the less products is the result of our stress. Ultimately, we don't want to know about the stress. We want to know how to return back to equilibrium. Well, to get back to equilibrium, we have to make more products, or we have to shift back to our products. So to get back to equilibrium, we shift towards our products, or we shift in the forward direction. That's the exact same thing that our table tells us. If you remove a product, which we remove the ozone in this case, then the reaction is going to shift forward or towards the products. Let's look at what happens if you increase the temperature in this reaction. Now, in order to figure out which way our reaction is going to shift, we first have to identify whether or not our reaction is an endothermic reaction or an exothermic reaction. In this case, our reaction is an endothermic reaction, We know that it's an endothermic reaction because we see plus heat on the reactant side. If you see heat on the reactant side, you can think of heat just like a reactant. So increasing the temperature would be the same thing as increasing a reactant. So again, if we use our teeter-totter or seesaw method, if we add temperature or increase temperature, that would be the same thing as adding a kid to our reactant side. So that is the result of our stress. Ultimately, we don't care about the stress. What we care about is how do we get back to equilibrium. So in order to get back to equilibrium, we need to have more products. So we're going to shift towards the products or in the forward direction. If we look on our table, under endothermic reactions, increasing temperature, we see that to get back to equilibrium, we do have to shift towards the products or towards the forward reaction. Let's look at what happens when we're increasing the size of the container. Well, if you increase the size of the container, the ultimate goal is for your reaction to go toward the side that has the greater number of moles of gas. So if I look at my balanced chemical equation, I have 3 moles of oxygen gas on our reactant side and only 2 moles of oxygen gas on our product side. So if I increase the size of my container, my rule says that I want to shift toward the side that has the greatest number of moles of gas. In this case, our reactants have the greatest number of moles of gas. So our reaction is going to shift towards the reactants or towards the reverse. The last stress that I want to talk about is adding a catalyst. When you add a catalyst increases the rate of both the forward reaction and the reverse reaction. So the result of adding a catalyst is actually no change, because the definition of an equilibrium reaction is a constant ratio of the rates of the forward reaction and the reverse reaction. So by adding a catalyst, there is no change. Let's talk about how we're going to apply this to the lab. We're going to keep our changes and we're going to look at our lab table. One of the things that you're going to be asked to do before you come to lab is to make a prediction based on your understanding of equilibrium. So each reaction involves a stress. So the first stress that we're going to look at is what happens after the addition of SCN minus. Well, when I look, SCN minus is a reactant. So if I add a reactant, that's the stress. But to get back to equilibrium, I need to shift towards the product side. And the product side, we say, is the forward. The next part of the question says, well, what color do you predict to see? Well, if my reaction is going in the forward direction towards the products, that means that I'm going to be making more products, and the color of the products is red. So I would predict that the color that I would see would be red. Let's look at the second one. What would happen after the removal of Fe3+? Well, Fe3+ is a reactant. So if I remove a reactant, my seesaw or teeter-totter would go up on the reactant side because I would have less of it. So to get back to equilibrium, I would need to make more reactant. So the way that I make more reactant is to go into the reverse direction. So what color would I predict to see? Well, if I'm going in reverse, that means that I'm going to be making more reactants. According to my sheet, that means that reactants are yellow. So the color that I would predict to see would be yellow. In the lab itself, you're going to actually do these chemical reactions, and you're going to see an actual color change, and based on your color change, you're going to say which way did the reaction actually shift. The last part of the lab is for you to state, did your prediction match what you saw in lab?